there were lots of campus Ethernets because they were really easy to deploy, and you could put them in a department, and then you could run a wire between two departments and you had a bigger network. And so we'd grown up networks sort of by agglomeration in lots of different university campuses, and NSF came up with some money, said, oh, we've got a little bit in our budget where we could get some 56 kilobit lines and tie those campuses together. And they did that, made the NSF Net Phase 1. But now you're tying together 10 megabit campus infrastructure with 56 kilobit wires, and it was wildly popular because people that couldn't talk could suddenly talk, and they're sending emails and moving huge files, and just everybody's really excited about this technology. But any one of those campuses could oversubscribe the net by a factor of 1,000. So we had a lot of packets piling up and getting dropped. At the time, I was a researcher at Lawrence Berkeley Lab, which is in the hills up above the Berkeley campus, and I was also teaching on the Berkeley campus. Even back in those days, which was mid-'80s, we had for every class there was a messages group, like a little news group that was set up. All the assignments would be put online, and I was trying to get course materials from my office in LBL down to a machine in Evans Hall at Berkeley, and there was like zero throughput in the net. It was one packet every 10 minutes or so, and it seemed unbelievably bad. And I went down and talked to Mike Carrolls, who was heading the BSD group, the people that develop Berkeley Unix, and he's getting reports of these problems from all over the country. From in those days, the easiest way to start running TCP/IP was to bring up Berkeley Unix, because there was a ARPA-funded, very nice implementation in it, and everybody was seeing poor performance. So we talked for a long time that day and on succeeding days about, well, what's going wrong? That is there some mistake in the protocol implementation? Is there some mistake in the protocol? This thing was working on smaller scale tests, and then it suddenly fell apart. I think we struggled for 3 or 4 months just going through the code, writing tools to capture packet traces and looking at the packet traces and trying to sort out what's breaking. And I remember the two of us were sitting in Mike's office after we'd been pounding our head against the wall for literally months. And one of us, I can't remember which one, said, the reason I can't figure out why it's breaking is I don't understand how it ever worked. We're sending these bits out at 10 megabits. They're zipping across campus. They're running into this 56 kilobit wire. We expect them to go through that wire, pop out on the other side, go through. How could that function? That turned out to be the crucial starting point. That at that point, we started saying, well, what is there about this protocol that makes it work? How does it deal with all of those bandwidth changes? How does it deal with the multiple hops? So this picture, that direction is time, this direction is bandwidth. So that's a fat pipe and that's a skinny pipe. And the scale at the time is, this is a 10 megabit pipe and this is a 56 kilobit pipe. So here the difference is about 3 to 1. It was really closer to 100 to 1. And so time, seconds times bits per second equals bits. So each of these little boxes in there is a packet. It's the number of bits in a packet. And if you scrunch it down in bandwidth, it's got to spread out in time because the number of bits doesn't change. And so, see the burst of packets, a window's worth of packets gets launched. It's going to fly through the net till it hits this fast to slow transition. And then, because the packets have to stretch out in time, they'll have to sit there and wait as they're fed into the slower wire. And they pop out the other side. They get spread out by this bottleneck, by the slower wire. Once they're spread out, they stay spread out. Right? There's nothing to push them back together again. They hit a receiver. It turns every data packet into an ACK. So you've got a bunch of ACKs that are going back towards the sender, and they remember what's the right spacing for that bottleneck. So the ACKs get back to the sender, and every ACK gets turned into a data packet. So we can see the data packets flowing back. And this is after one round trip time. Now the packets are coming out perfectly spaced, so they go by, a new one goes into the net in exactly the time it takes a packet to exit from the bottleneck. So these ACKs are sort of acting as a clock that tells the sender when it's safe to inject every new packet. And they're always going to be spaced by whatever is the slowest point in the net.
And the key thing is how can you get to steady state sort of most quickly without wasting?
Yeah, and the issue, the failure we saw was this works perfectly after you've exchanged a round trip time worth of packets. But when you're starting up, when you're here, there's no clock. And so the hard part on TCP is not getting it running, it's getting it started. Because once you've got it running, you've got a clock that tells you exactly what to do. So if you turn them on, suddenly you get in this repetitive failure mode where you saturate the buffering that was available at some gateway, and then when you retransmit, you do the same thing again, so you're always losing packets. But if you turned it on more gradually, then you wouldn't overload the buffering, and you'd get enough of a clock going so that you'd control the amount of backlog to fit the available buffer, but you'd still be growing the number of packets in flight so that you'd eventually get you start with a kind of sporadic clock, but you'd eventually fill in the details and get a per packet clock.
How did you get it to the point where it was in all the TCP/IP implementations on the planet? Because they kind of have to cooperate in a way.
So remember, it was a much simpler time when you're talking about all the TCP/IP implementations on the planet. At that time, there were like 4. So there was the Berkeley Unix one, there's the MIT PCTCP, there was a BBN one that was used in butterflies and imps, and there was a Multics one. I took the couple of TCP kernel modules that we'd been working on, packaged them up in a tar. I had this horrible driver hack that would let us snarf packets from the kernel, and I mean, it was really a horrible driver hack. It was the way you said what you wanted to snarf was by ADB in the kernel. You wrote in binary some new values. These are the ports that I want to look at, and the driver would capture those into a circular buffer, and you'd read kernel memory to pull that buffer out. Craig Laris and Chris Tork, who were working in my group at LBL, and we're both longtime kernel hackers, were just embarrassed at this, and they put together a really nice, clean driver thing called BPF, the Berkeley Packet Filter, that would let you pull packets out of the kernel via a very efficient I/O control interface. And so we bundled all of that up, and on the TCP/IP mailing list, which in those days was, TCP/IP was very experimental. It was very leading edge, and pretty much everybody who was playing with it was on that mailing list. So announced that this stuff was available. A bunch of people FTP'd it, tried it, it blew up. sent kernel core dumps and bug reports and fixed the bug reports and put new versions out. And somebody would immediately come back and say, panicked here, do you want the K core? And I go, oh, no. Embarrassed. Put out a new version, go out, somebody else would come back and say, panicked here, and fix that, and just cycled like that. And after about a day, we got a version that didn't immediately panic, and then started working on the actual algorithms and a little bit of tuning to make sure that it actually did good all the time and didn't do any harm. Just completely a community effort, and sort of when the community was saying this mostly does good and never seems to do harm, that's pretty much what Mike needed to put it into the kernel. So he took the community developed modules and rolled them into the BSD release.